Assalamu alaikum. I am Asad Yusuf. Welcome to MPTF channel. Today's topic of presentation is LINAC components and operation, and I'm focusing on Elekta LINAC. The literature, the presentations or video presentations available online are very rare for Elekta LINAC, so I thought it's good to share my own experience and the content which I have. So these are the contents of my presentation. Architecture of Elekta LINAC. This is a traveling waveguide, electron gun, steering coils, and this is the bending magnet system of Elekta. So we'll start with a modulator. It's a power supply to the magnetron and to the electron. So the pictures in this presentation will help you to identify the components of the machine. Magnetron. A magnetron is an RF oscillator that extracts the microwave energy from electron by placing a resonant structure in a magnetic field. This is its look like. This is the electron gun. This is the magnetron cavity, RF cavity, and this housing is placed here, and magnetron housing in this way. So this is the working principle of magnetron. As you can go through that. I'm not gonna go into detail of it right now in this presentation. The RF waveguide. The RF microwave power generated by a magnetron is conveyed to the accelerated structure via waveguide. These are the gas-filled metallic structure, either rectangular or circular in a cross-section. And these are the placement of RF waveguide. Accelerated system. The vacuum system provides the extremely low pressure needed for the operation of electron gun. Accelerating waveguide, bending magnet flight tubes. Without a vacuum, electron would interact with air particle, resulting in energy losses and deflection of the electrons. It would influence, accelerated by a localized field, again interact against the wall, creating avalanche situation, which could cause damage to the entire system. The vacuum system operates at 10 to the power 7 torr. The pressure of vacuum in traveling waveguide is less than the pressure of vacuum in a standing waveguide. So this is an important point to remember, the difference between the two LINACs. The mean free path length need to be a longer for traveling waveguide. Ion pump used to create a vacuum have a strong external permanent magnet, around 5 to 7.5 kilovolt cathode and multi-cell anodes. There are two ion pumps in a LINAC, a larger pump for the body of the waveguide and a smaller pump for the gun region. So on Elekta, we need to monitor these two vacuums values for the ion pumps, because if they drop, then the functionality will be affected. The pressure system pressurized the RF waveguide system with the sulfur hexafluoride SF6 insulating the waveguide and preventing the electrical breakdown of the high power microwave electric field. The gas not only reduced the RF arcing but also helped to cool the output glass dome of the magnetron. A water cooling system is also in place. Temperature control is critical for the accelerator structure. It also serves to remove heat dissipated by other components. So this is the ion pump. The vacuum port is attached. The ion pump is a hole. And this is the water filter location. The electron gun. The electron gun is a source of the treatment beam. It contains a spiral wound heated tungsten filament mounted in a conical cathode structure form, which the electrons are thermally emitted. The electron emitted are focused into the pencil beam by focusing the electrode and accelerated through the anode into the waveguide. The electrostatic fields used to accelerate electron is generated by a high voltage pulsed power supply from the modulator. Accelerator structures. Elekta waveguide is just over 2 meters in length and is divided into cell by Eris disk, each with a central hole. The accelerating waveguide make use of cavity principles, where the energy from the electric field generated by a cavity is transferred to the accelerating electron beam. Both the RF and the electron injected by the gun arrive at the first cell at approximately 0.4 speed of light. The first few cavities vary in spacing and geometry of iris plate following the RF and the electron to accelerate to close to the speed of light. The later cavities are uniform in the size and provide a constant velocity of traveling wave. With the further energy transfer into the cavity fields going to the relativistic mass energy, as electrons gain energy along the length of the accelerator structure, they accelerate until they reach the relativistic velocity of 0.998 c. So this is the waveguide, a traveling waveguide, and this is the axial view of if you cut from the middle or slice, you can see the iris disc and the hole. Bending magnet. After the electron beam exits the waveguide into the flight tube that is located between three electromagnets that comprises the bending system. The bending magnet used in these machines as 112.5-degree double focusing Salem band system. It is the only used in traveling waveguide system. It's a seldom, I believe, which might be a spelling mistake, due to the reduced demand on the beam focusing and narrow guide dimension. There are three bending magnets in the system. First bend through 45 degree, the second through another 45 degree, and the third through 112.5 degree to point the beam down at 90 degree to the target. The path of the beam is determined only by a magnet, not by the flight tube. The three connected in a series with the main current being the bending course. The last magnet has a current bending fine. The bending course and bending fine current need to be optimized during the setup of the correct beam trajectory and the beam energy for each energy available. So this is a flight tube, you can see, and in the flight tube these magnets are in place. Target and shift method. The flight tube mentioned above as a tube in which electrons travel as they are focused by a bending magnet is able to shift it within a LINAC without affecting the electron beam. Within this, allow the accurate positioning of either X-ray target or an electron window at the top of the treatment head to enable each mode of operation. For an electron beam, a thin nickel window is positioned, so the electron can centrally pass through into the treatment head. To generate a photon beam, an electron beam is incident on 1 mm thick tungsten target produce a symmetrical photon output after Brownstalling radiation. When the electrons strike the target, a small portion of energy converted into Brownstalling photon. The rest of energy release is a heat. Due to the large inefficiency in the conversion, the target has to be water-cooled. So this is the target, and this is where it is located. And this is the flight tube. You can see the flight tube is connected with the target. So the electron beam is coming from here. So this is the inverted view, basically. So primary filter system. This is what it look like. Tantalum scattering foil of drifting electron thickness. And there is an open board for the photon beam. This is what the original use look like. Secondary filter system, which include the flattening filter, and this is the placement of flattening filter. This is the size you can see, and this is a scattering foil for high energy, of course. But the low energy is different, as I don't have any picture of that. This is the ion chamber position. Ion chamber scattering foils are here. So then the gantry is 180 degree, you can see, and these are the below, and these are the in front of it. And this is a systematic diagram of ion chamber. Shutters. An aluminum alloy shutter or backscatter plates of 3 mm thickness located directly below the ion chamber. The shutter is present in the path of the beam for all the photon treatment. Its purpose is to reduce asymmetric backscatter from the wedge into the ion chamber. By having the shutter in place for all photons treatment wedge or open, it also ensures the constant amount of backscatter to the ion chamber. The shutter is removed from the path of the beam of electron treatment. So this is a wedge which is on the gantry head of Elekta machines. It's a motorized wedge. Usually it's out of the field. MLC system. So Elekta are using agility system, and this is this look like the primary collimator, the flattening filter, the ion chamber, and the upper jaw act as MLC, and the lower jaw is a backup, is kind of backup diaphragm and X diaphragm. So the Y jaw are the MLCs in Elekta machines, and this is the agility picture. The placement of system is here on gantry head. And the applicators, this is look like a different sort of applicators as compared to Varian. So thank you for the listening of this presentation. I hope you have got good information about the Elekta LINAC. The second presentation will be again about the Elekta LINAC, but more focusing on the dosimetry aspects, how the beam profile shifted when it was tuned by the engineers. Those pics will help you understand the function of playing with voltage and current and focusing the beam on the target. So thank you very much. If you guys have any question, you can put on the comments.